Hello, welcome to 3.3, increasing and decreasing functions in the first derivative tests. Definition of an increasing and decreasing function. We should know what this is already. I think we talked about this in pre-calculus. A function f is increasing on the open interval if for any two numbers x, there should be a sub 1 and x sub 2. In the interval x1 is less than x2, it implies f of x1 is less than f of x2. Function is decreasing though on the interval for x1 and x2. If f of x1 being less than x2 implies f of x1 is bigger than f of x2, that means it's going down versus going up. A function is increasing if, as x moves to the right, the graph moves up, and is decreasing as the graph moves to the as x goes to the right, it's going down. Test for increasing and decreasing functions. Ready for this? Let f be a function that is continuous on the closed interval from a to b, and differentiable on the open interval from a to b. If the first derivative of f is positive for all values in the interval, then it's increasing. So if your derivative is positive, you have a positive slope, means it's going up. If your first derivative is negative on the interval, it means it's decreasing. If your first derivative is negative, it means you have a negative slope, so it's going down. And if your first derivative is 0, that means it's a constant function. Just if it's 0 for a whole interval, that means you have a horizontal line. So example 1 says find the critical numbers of f of x equals x squared minus 6. Find the open intervals on which the function is increasing and decreasing. So our first derivative is going to be 2x minus 6. So we take 2x minus 6 and set it equal to 0. 2x equals 6, or x equals 3. So there's our critical number. So we have two intervals. It's going from negative infinity to 3, and then from 3 to infinity. We want to look at these two intervals. On one it's going to be increasing, on the other decreasing. You could probably guess by knowing what the shape is going to be as to which one is going to be, where it's increasing, where it's decreasing. So I build this little chart. We have our interval. Negative infinity to 3, and then 3 to infinity. We'll have a test value from each interval. So give me a number between negative infinity and 3, and if you said 0, we were thinking like. Give me a number between 3 and infinity, we'll go with 4. Okay, so we'll look for the sign of f prime of x. So f prime of 0 is going to be 0. Let's choose a different value. Oh, f prime here. That's negative 6. So it's less than 0. F prime of 4, that's going to be 2 times 4 is 8. 8 minus 6 is 2. That's positive. So conclusion. In this interval, because the first derivative is negative, f is decreasing. In this interval, because f prime is positive, f is increasing. So f of x is increasing on the interval from negative infinity, from 3 to infinity. F of x is decreasing on the interval from negative infinity to 3. What we have here is a parabola. There's 0. There's 6. So right in between there is 3. So it's decreasing to that point, and then it's increasing. I'll say this. F of x is neither increasing nor decreasing at x equals 3. Okay, let's go on to the next page. Guidelines for finding intervals on which a function is increasing or decreasing. Let f be continuous in the interval from a to b. To find the open intervals on which f is increasing or decreasing, use the following steps. Locate the critical numbers of f in the interval from a to b and use these numbers to determine the test intervals. So you find the critical numbers. That's what we did. Take the first derivative, set it equal to 0. Determine the sign of f prime of x at one test value in each of the intervals. And use the test for increasing and decreasing functions to determine whether f is increasing or decreasing on each interval. These guidelines are also valid if the interval ab is replaced by the interval of the form negative infinity to b, a to infinity, or negative infinity to infinity. Now, strictly monotonic on an interval, it's a function that is either increasing or decreasing on the entire interval. Monotonic. And I've never known if it's actually pronounced monotonic or what, but I call it monotonic. Okay, the first derivative test. Let c be a critical number of a function f that is continuous on the open interval f containing c. If f is differentiable in the interval except possibly at c, then f of c can be classified as f prime of x changes from negative to positive at c, then f is a relative minimum. If f prime of x changes from positive to negative, here's a positive negative, we have a relative maximum. So if you go negative to positive, we have a relative minimum. But if f does not change sign at c, so it goes, like in this case, it goes up, becomes 0, goes up again, f of c is neither a relative min or a max. It's like a saddle point. Example 2, find the relative extrema of f of x equals x squared minus 6x. We saw this one before. Our f prime of x is 2x minus 6. 2x minus 6 equals 0. 2x equals 6. X equals 3 is our critical number. So from negative infinity up to 3, we found that f prime of x was negative. That was from our previous example. So it's going down. From 3 to infinity, f prime of x was positive. That means it was going up. So x equals 3. If it went down then up, that must mean it's a low point. It's a relative minimum. So f of 3, go back to the original function, is 3 squared minus 6 times 3. You're going to get negative 9. So 3 negative 9 is a relative minimum. So that's a relative min. That's a low point. And remember we had the parabola. That would be the vertex of the parabola. That was the low point. Okay, example 3 says find the critical numbers of f of x equals x to the 1/3 plus 1. Find the open intervals on which the function is increasing or decreasing and locate all relative extrema. So our f prime of x is going to be 1/3 x to the negative 2/3, which is just 1 over 3 x to the 2/3. So where is 1 over 3x to the 2/3 equal to 0? Well, nowhere. So, but it's not defined at x equals 0. So x equals 0 is the only critical number because it's not defined there. So we have our interval from negative infinity to 0, and then from 0 to infinity. Let's get a test value. I go -1 here and +1 there. The sine of f prime of x. We put -1 in here. It's going to be 3 times -1 to the 2/3. That's like -1 squared, which is 1, and the cube root of that's 1. So it's 1 over 3 times -1 to the 2/3, which is 1/3, and that's positive. Put in +1, you're going to have 1 over 3 times 1 to the 2/3, which is 1/3, and that's still positive. So our conclusion is that it's increasing here, and it's increasing in the next interval. So it's always increasing. It's like going up, kind of hesitates, then goes up again. It's never decreasing, but we have this one place where that wouldn't be defined. So the function is increasing on the interval from negative infinity to 0, union 0 to infinity. There are no relative extrema. Okay. I'm going to go on to example 4 here, so pause if you need to pause. Okay, on example 4, let's just consider the function on the interval from 0 to 2 pi. Find the open intervals on which the function is increasing or decreasing, and locate all relative extrema. Oh, I didn't have a function. Let's say f of x equals x over 2 plus cosine of x. That means f prime of x is going to be 1/2 minus sine x. So if you say 1/2 minus sine x equals 0, that means 1/2 equals sine x. Okay, that means that x would have to be pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6, and we're doing from 0 to 2 pi, so we could stop there. So we'll have the interval we have 0 to pi over 6. We have pi over 6 to 5 pi over 6. We have 5 pi over 6 to 7 pi over 6. And then we have 7 pi over 6 to 2 pi. Oh, wait a second, I forgot. 7 pi over 6 is going to be negative 1/2, and so is 11 pi over 6. I need to exclude those. So let's just back this up a bit and make this go to 2 pi. Okay. Okay. Now we'll get our test value. From 0 to pi over 6, let's go with pi over 12. From pi over 6 to 5 pi over 6, we can go with pi over 2. 5 pi over 6 to 2 pi, we can go with pi. So let's look for the sine of f prime of x. So in the first case here, we're looking at 1/2 minus sine of pi over 12, and that's going to be positive. Here is 1/2 minus sine of pi over 2. That's going to be 1/2 minus 1, that's negative. Then we have 1/2 minus sine of pi. It's 1/2 minus 0, that's going to be positive. So our conclusion, being positive means it's increasing. Being negative means it's decreasing. Being positive means it's increasing. So it's increasing on the interval from 0 to pi over 6 and the interval from 5 pi over 6 to 2 pi. And it's decreasing from pi over 6 to 5 pi over 6. So we're seeing it's going to be increasing, then decreasing, then increasing. So this value here was at pi over 6, and this is at 5 pi over 6. That means going to pi over 6 it increases, at pi over 6 it turns to decrease. So that means this must be a maximum value. At 5 pi over 6 it's going down, 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 hits 5 pi over 6, starts going up. That means 5 pi over 6 must be a minimum. So if we look at f of pi over 6, we have pi over 6 over 2 plus cosine of pi over 6. And that's going to be pi over 12 plus the square root of 3 over 2, which gives us a relative maximum. F of 5 pi over 6 is going to be 5 pi over 6 divided by 2 plus cosine of 5 pi over 6. That's going to be 5 pi over 12 minus square root of 3 over 2. So our relative max is going to be located at pi over 6, comma, pi over 12 plus the square root of 3 over 2. And the relative min is going to be located at 5 pi over 6, comma, there should be 12 there. 5 pi over 6, comma, 5 pi over 12 minus square root of 3 over 2. I'm going to go on to the last page then. We have one more example to do. A little bit of algebra. Okay, the electric power P in watts in a direct current circuit with two resistors R1 and R2 connected in series is P equals V times R1 times R2 over R1 plus R2 squared, where V is the voltage. If V and R1 are held constant, what resistance R2 produces the maximum power? So we're going to find the derivative with respect to R2 of P. That's the derivative with respect to R2. I always want to say D2, and a Star Wars guy in me. Of VR1 R2 over R1 plus R2 squared. So that's going to be the quotient rule. Low, which is R1 plus R2 squared times D high, this derivative is just going to be VR1 minus high VR1 R2. D low would be this derivative, so it would be times 2 times R1 plus R2 times 1. all over the square of what's below. R1 plus R2 squared. So P prime is going to be, from here, that's like an R1 plus R2 times R1 plus R2 times VR1 minus VR1 and R2, the two out front, times R1 plus R2 over, down below, that's an R1 plus R2 times R1 plus R2. And of course, you could factor one of these out. It divides out. So what we have then is R1 plus R2 times VR1 plus 2VR1 R2 over R1 plus R2. Oh, I made a mistake. That needs to be squared. So that would have been the fourth power. You got that cubed left over. There we go. So P prime is going to be V, if you distribute that, R1 squared plus VR1 R2 minus 2V R1 R2 over R1 plus R2 squared, cubed. That's going to be VR1 squared minus VR1 R2 over R1 plus R2 cubed. So set the numerator equal to 0. Where is VR1 squared minus VR1 R2 equal to 0? That's where VR1 squared equals VR1 R2. If we divide both sides by VR1, V's divide out, the R1's divide out, and we have R1 equals R2. So where the two resistors are equal, we have maximum power. That'll do it for 3.3. I hope you enjoyed this section. I hope you're learning something from this and applying this. And send me your questions. Thank you.